everyone. Welcome back to the lectures on Introduction to Multi-Agent Systems. In today's lecture, we'll introduce the topic of nonlinear systems. Now, nonlinear systems are all around us. They can be found very commonly. Some examples would be cars, fixed-wing aircrafts, electrical circuits, population growth models, human interaction and collective decision-making in social networks, and so on. However, while they are ubiquitous, still, because nonlinear systems could be slightly more complex than linear systems, their analysis tools are a bit more intricate and could be more challenging. In today's lecture, we'll introduce what exactly is a nonlinear system, how is it different from a linear system, and what are some of the tools using which we can actually analyze nonlinear systems. So let's get started.
Nonlinear systems are all around us. In fact, most of the real-world systems are actually nonlinear. So what are some examples of nonlinear systems? Some examples would be cars, fixed-wing aircrafts, electrical circuits, with components like diodes turn out to have nonlinear models, as an example. Then population growth models, human and collective decision networks, etc. These are only some examples of real-world systems which tend to have models which are nonlinear in nature, or all of these systems' behaviors can actually be described much more efficiently or better using nonlinear models. Well and good, now we know that nonlinear models can do a good job in representing systems. However, we still face a challenge while using them. The challenge is being that the analysis of linear systems tends to be slightly more easier relatively. So let's write it. Challenges. The challenges are that the analysis of nonlinear systems is relatively more non-trivial. Furthermore, the analysis tools for the nonlinear counterpart are significantly different. As compared to the tools that we use for linear systems. There are some more challenges beyond the analysis. Some practical challenges. One of the major issues is the existence of multiple equilibrium points. What is an equilibrium point is something we'll discuss in a short amount of time. But for now, to understand it in a simple way, we would say that an equilibrium point simply represents a point which we generally tend towards at steady state. However, sometimes these equilibrium points could be stable or unstable, meaning while when we reach an equilibrium point, we tend to stay on it. However, we move towards it only when the equilibrium point is a stable one. When it is unstable, any slight perturbation from the equilibrium point will actually take us much farther away. These kind of behaviors do not occur for linear systems. So let us write one more challenge. Existence of numerous intricate behaviors which do not occur for linear systems. So what are they? First is a finite escape time. What is a finite escape time? A finite escape time says that the system actually takes or goes to infinity in a finite amount of time. So you can see a quick example. Let us look at the system shown here. X star equals 1 divided by t minus 5. In this system, as t approaches the value 5, we see that x dot actually becomes equal to infinity, meaning the states of the system also blow up to infinity. And this occurs in only a finite amount of time. That is, in the case of a linear system, x dot will take infinite amount of time to reach the value of infinity in general. What are the other behaviors that can occur in only a nonlinear system? Yet another behavior is that of a limit cycle. Limit cycles represent oscillatory behaviors in the system such that the amplitude and frequency of the oscillation is actually independent of the initial condition from where the system starts, which is quite different from the linear counterpart, because in linear systems can also exhibit oscillatory behaviors. However, the amplitude of the oscillation depends on the initial conditions of the system. So all of you must have studied it in some basic control course, so that's why we are not going into the details of this. What are the other behaviors that it can experience? It can also experience something that's known as bifurcation. What is bifurcation? So we discussed some time back that an equilibrium point is that particular point in the system such that if the trajectory starts there, then it continues to remain there. It cannot move away from it. In general, nonlinear systems can have multiple isolated equilibrium points, which is something that a linear system cannot have. In a linear system, we either have just one equilibrium point or a continuum of them. Why do we say a continuum? Let's try to understand this a little bit. Let's try to distinguish here between a linear and a nonlinear system. If it is a nonlinear system, in that case, the system can have equilibrium points spaced apart like this. Let's just write it E1, E2, E3, E4, and E5. And as we discussed, the behavior of the system around these equilibrium points again leads to a very interesting phenomena in the case of nonlinear systems. The point is, if we start exactly at T1, we will continue to stay there. That is the definition of an equilibrium point. All of the derivatives of the state go to 0 at the equilibrium point. However, if it is a stable equilibrium point, and furthermore, if we start from any point outside of the equilibrium point, and if we lie very close to it, then we always move towards the equilibrium point if that particular equilibrium point is a stable equilibrium point. However, consider an equilibrium point which is now unstable. If it is an unstable equilibrium point, we will move away from it if there's any slight perturbation. So basically, in the region close to the equilibrium point, if the trajectory moves towards the equilibrium point, then it's a stable equilibrium point. If you're very close to the equilibrium point and the trajectory rather moves away from the equilibrium point, then it is an unstable equilibrium point. So this is a stable equilibrium point, and this here is an unstable one. What happens in the case of linear systems? Let's see. So suppose, let us assume a simple autonomous linear system given in this manner, where A here is a square matrix. In order to calculate the equilibrium points, we look for points where the derivatives of states go to 0. Hence, we simply set x dot being equal to 0. Then what exactly are we looking for? We are simply trying to find out the roots of the equation ax equals 0, which gives us nothing but a set of simultaneous equations. However, what is of interest to us is this. This implies that any x which belongs to the null space of A, or for every x belonging to the null space of A, we have x dot is equal to 0, meaning we know that a null space is in fact a subspace which can have a dimension sometimes greater than 1 as well, meaning we either have, if the null space has a dimension of being equal to 0, meaning x equals 0 is the only point for which ax goes to 0, then the dimension of the null space is equal to 0. In that case, there's just one equilibrium point, which is x equals 0, the origin. However, whenever null space has a dimension greater than or equal to 1, we get every point in the null space being an equilibrium point, meaning we now have infinitely many equilibrium points. However, something that can never happen in a linear system is this. We see here that there are multiple equilibrium points. However, all of these equilibrium points are actually spread apart. This is something that we can never get in the case of a linear system. While in a linear system, you deal with a state space model, which is also linear in nature. The same doesn't hold for the case of nonlinear systems, meaning the state space representation of a nonlinear system now takes the following form. Let x be the n cross 1 state vector, then x dot, which is equal to some x1 dot up to xn dot, is equal to something in this form. F1, which is a function of x1 to xn, meaning all of the states, and the parameter time t, which is the independent variable, and some external input or some input to the system u. Similarly, for the nth state, this is given as fn. x1 to xn t u. So when we say state, we mean exactly the same thing as we meant in the case of a linear system. Meaning, if we now want to define it, we would say state is the memory that a dynamical system has of its past. This is what is the state of a system. Now let us quickly look at a mathematical state space representation of a practical system. Consider something that's known as the logistic population model. In the logistic population model is expressed in this manner. X here again represents the population of the region. X is the state, which is in fact a scalar in this case. And dx by dt, the state space representation, is given by Ex times 1 minus x. This is a simplistic representation of the logistic population model. And how do the states vary with time in this case? This is how the trajectory of the system. So the trajectory simply means how the states evolve over time. Or we can say the state x. This is how we can see it varies with time. We see that eventually the states do stabilize at a value being equal to 1. So this is a real world, more or less a realistic example of a nonlinear model of a system. We'll also formally now define what is an equilibrium point, and soon after, we'll try to calculate what are the equilibrium points of this system. Before that, let us define the notion of an equilibrium point. Given a nonlinear system, whose state space representation is x dot of t is equal to f of x of t comma u of t. It could also be an explicit function of t as well. And yt, which is the output of the system, is again a nonlinear function of the states and the input. So what is an equilibrium point? At an equilibrium point, x bar, we get x dot of t at x equals x bar is simply equal to 0. So now, this is what happens to the first derivative. What happens to all subsequent derivatives at x equals x bar? What happens to x double dot, x triple dot, and so on and so forth? I'll leave the answer to this at. Suppose our initial condition now is equal to x at t equals 0 is equal to x bar. What happens then? This implies that x of t remains equal to x bar for every t greater than equal to 0. This is the most important point. It simply means that, so when we set this equation here, x dot is being equal to 0, remember that it goes equal to 0 also at some suitable value of the input, u of t, being equal to u bar. Now, when we come back to this expression, suppose we start at the initial condition, xt equals 0 being equal to x bar, then when that particular input, u bar, is applied, we know that for all time to come, the states continue to be at that equilibrium point. A simplified notion of this can be given for something that's known as an autonomous system. In an autonomous system, so first of all, let us write it what it looks like. In an autonomous system, the state space representation is given as this: x dot of t is equal to simply f of x comma t. This is the autonomous system. The f simply here depends on these states. Hence, the system does not depend on either the time parameter or any external input and behaves autonomously. Hence the name, an autonomous system. So how do we go about calculating the equilibrium points? We can do the same thing that we've been doing before. So equilibrium points are given by setting x dot of t equals 0. This implies f of x equals 0. Hence, the equilibrium points, let's denote them as x bar. They're simply the roots of f of x equals 0. Since x bar is an equilibrium point, by definition, if the initial condition, let's say x at t equals 0, suppose it is equal to some x0, if we set this x0 to be equal to our equilibrium point, then x of t continues to remain at the equilibrium point for every t greater than or equal to t naught. Let us look at an example of this. A good example of an autonomous system would be a logistic population model. A simplified version of this model is given as x dot equals ax times 1 minus x. So how do we figure out the equilibrium points? In order to calculate that, so this is the model, and the equilibrium points are achieved by setting x dot equals 0. This implies ax times 1 minus x is equal to 0. Hence, the equilibrium points x bar are equal to 0 or 1. So in this lecture, we have now introduced a lot of properties pertaining to a nonlinear system. Especially we have introduced a very important notion, that is of an equilibrium point of a nonlinear system. In the next lecture, we'll try to understand when is a nonlinear system stable. Equivalently, when are its equilibrium points stable and when are they unstable. Thank you.